How's it going, ladies and gentlemen? Mr. Donahue here, looking to go over 9.7 problems having to do with molecular orbitals. So 26 says the bond order of any molecule containing equal numbers of bonding and anti-bonding electrons is blank. All right, we need to know the bonding order formula, which is 1/2 in parentheses the number of bonding electrons minus the number of anti-bonding electrons. So the question is asking, well, if the bonding electrons equals, X minus, if they're equal to each other, what would you get as a bond order? It would have to be 0. Now you may be asking, all right, well, I still kind of a little fuzzy on the difference between a bonding orbital and an anti-bonding orbital. So on the screen, I posted a picture that I got off the interwebs and to help illustrate what's going on. So here are the bonding orbitals. For sigma bonds, for the s orbitals, they just kind of loop together, right? Those two dots represent the nuclei, and those orbitals come together, and that's a bonding orbital. There's also the anti-bonding orbital, which does the exact opposite. And you can think of it this way. These are orbitals for electrons. Electrons are negatively charged. They should repel each other. So you can think of them as being, well, they can come together and form a, bonding orbital. They can group together, or they can repel each other in an anti-bonding manner. So sigma bonds for the p orbitals look really similar, right? So we got those lobes that are going to overlap in between the two nuclei. That's definition for a sigma bond. It's going to be between the two nuclei. Anti-bonding would be, again, them repelling each other kind of and flattening out because they're both negative and kind of repelling each other. So that would be anti-bonding. They're doing the opposite of bonding. The pi bonds, again, would be above and below the plane in between the two nuclei. They're not going to be in between them. They're going to be above and off to the sides. So bonding, they, again, loop together, kind of forming one big thing. And anti-bonding, they're repelling each other. Now, the d orbitals, same concept. I don't think the visual helps as much, but you can see that they're repelling each other. That's why they're not bonding here. It's empty. They're repelling each other. Same with up here for the anti-bonding. And the bonding ones, they come together. 27. In comparing the same two atoms bonded together, the blank, the bond order, the blank, the bond length, and the blank, the bond energy. There's a lot of blanks, so let's just kind of check a couple of them. All right, well, let's say if we increase the bond order, then the bond length should go down, right? If we're having a double bond that's shorter than a single bond, and the blank, the bond energy, well, the bond energy should go up, right? Stronger bond holding them together. And let's say the opposite. The blank, let's say the lower the bond order, then the greater the length should be. Single bonds are longer than double or triple bonds, and the lower the bond energy. So which one of these things works out? Smaller, longer, and smaller. So the smaller the bond order, the longer the bond length, and the smaller the bond energy. 28. In molecular orbital theory, the sigma 1s orbital is blank and the sigma 1s antibonding orbital is blank in the H2 molecule. So these molecular orbitals, well, what's going to happen is for each of the H's, they're putting in their 1s. So they're each putting in one atomic orbital. So we should get 2 molecular orbitals. We're going to have our sigma bonding, and we're going to have our anti-bonding molecular orbitals, right? So they're both putting in an orbital. So you're going to get a bonding orbital and an anti-bonding orbital. If they both were putting in 3 orbitals, then you'd have 3 bonding orbitals and 3 anti-bonding orbitals. So now we know the configuration for hydrogen is 1. So they're each giving in 1 electron. So where do we put them? Well, we always start with the lower energy. And the reason that we put the sigma bonding molecular orbital down below is because it has lower energy and you're going to fill it first. So we got to place 2 electrons, 1 electron, 2 electrons. So the sigma bonding is full. We can't put any more electrons in there. And the anti-bonding one is empty. Right? So which choice would that be? Choice B. And for, you know, poops and giggles, what's the bond order? Well, it'd be 1/2 the bonding electrons, which we got 2, minus the anti-bonding, which would be 0. So bond order would be 1. And what do we know about hydrogen bonded to hydrogen? It's a single bond. Awesome. 29. Based on the molecular orbital theory, the bond orders of the H bonds in H2, H2 plus, and H2 minus are blank respectively. So again, hydrogen. So they're each putting in one atomic orbital. So that's going to give us 2 molecular orbitals, 1 bonding and 1 anti-bonding. All right, well, let's take a look at how many electrons each thing has. H2 would have 2 electrons. H2 plus, what happened to that plus? It lost 1, so it only has 1 electron. And H2 minus means it gained an electron. That would have 3. So let's check them out one at a time. All right, I'm going to do a bond order formula up over here, which is going to equal 1/2 the bonding electrons minus the anti-bonding electrons. So I'm going to set it up 3 times for the 3 different molecules so we can just plug in our numbers. All right, let's start with the thing that has the lowest, right? This is going to be the H2 plus. Only has 1 electron. Where does it go? It goes in right here. That's where the first electron goes. So it's going to have 1 bonding and no anti-bonding electrons. So its bond order is going to equal 1/2. So let's go to H2 where there's 2 electrons. Where does that second electron go? It goes into that bonding orbital. So there are 2 bonding electrons and no anti-bonding electrons. So its bond order would be 1. Now let's check out where would this third electron go? Third electron would have to go into the anti-bonding orbital. So we have 2 bonding and 1 anti-bonding. So our bond order would be 1/2. So which one of these things is our answer? Choice D. So the reason that you don't see H2 plus or H2 minus as often as you see H2 is because the bond order is not as stable as in H2, because single bond more stable than half a bond. Yeah. And I think, yeah, that's it for 9.7. All right, this topic kind of a little funny. So there are videos on my blog to help with it. You know, check it out. Bring questions to class, and I will see you there.